Okay, thanks everyone for joining. We have a great presentation this morning by Andreas Getz on GPU computing and programming on Expanse. Before Andy gets started, I want to bring your attention to the Exceed Code of Conduct. Everyone's generally on good behavior, but if you do observe any inappropriate behavior, please let us know by reporting it to exceed.org/code of conduct. And Exceed is also trying to be sensitive to terminology used in these training events. If you do observe any inappropriate terminology or materials, please send an email to terminology@exceed.org. And with that, I will stop sharing and hand it off to Andy. Take it away, Andy.
All right, thank you, Jeff. Welcome, everybody. Thanks for joining. So let me share my screen. All right, can you see my presentation okay?
Yes, it looks good.
Okay, awesome. Yeah. All right, so welcome everybody. So this is a very brief introduction. We only have 1 hour, unfortunately. And so I hope I can give you a good overview of GPU computing and programming. So I have programming in there, so I want to take you briefly through also how to program GPUs. And then, of course, we have Expanse at SDSC, our new supercomputer, and to just briefly show you how to use Expanse GPU nodes. So, okay. So what I want to do with you is to quickly go over the following topics. So give you a brief overview of GPU hardware, short introduction to some examples of GPU accelerated software, and then I want to give you a short introduction about programming GPUs using libraries, Cuda C, so Cuda programming, and then OpenACC, and then we'll have a look at SDSC Expanse GPU nodes, how to get into those nodes, how to run GPU jobs, and well, developing GPU software, basically, you know, few quick examples on how to compile code and similar things. Now, I want to say, I don't know exactly what all your expectations are in coming in here, so please give us feedback, you know, if you want to hear more about Expanse and how, you know, practically get into the compute nodes and similar things, and less about overview of GPUs, or if you want to have more of the other, or if you want to have multiple webinars, any feedback would be good for us. So just briefly, you know, what is a GPU? Effectively, it's just an accelerator in some sense. You know, in the past, you know, we had different types of accelerators, and we still do have that. It's just a component that speeds up some aspect of a computing workload. And, you know, in the past, we would have had even floating point coprocessors in older PCs for floating point operations. And so it's a specialized chip. More recently, you know, there are field programmable gate arrays, specialized chips. But so the important piece here about the graphics processing units is that, you know, it's been driven by a massive investment in the gaming industry, which is approximately $150 billion per year. I think it's 180 billion last year. So there's a lot of money, and so that goes into development of these GPUs. And originally, they had fixed function pipelines. So some people who are older like myself, they will remember early GPUs that you actually couldn't program. And then at some point, so the first really programmable GPU was a GeForce GTX card. I don't remember if it was a 280, it might have been another one, but around that time by Nvidia. And, you know, they don't look any different nowadays, but, you know, you have GPUs, of course, not only that go into PCI Express slots, but also that are sitting as processors directly on the motherboard. The important piece is that they have a simplified core design compared to CPU, which means limited architectural features like branch caches and a partially exposed memory hierarchy that you actually should be aware of when you program GPUs. But also, even if you just use GPUs, you should know how the data moves between your CPU and the GPU. Now, why is there such an interest in GPUs? It has to do, you know, with microprocessor design over the trends that we have seen over the last 20 years, I would say. So this is not fully up to date, but effectively what's on this plot is still holding today the microprocessor trend data. And you're probably all aware of Moore's law that the transistor count in integrated circuits doubles about every 2 years, and that exponential growth still holds. So that's that yellow brownish dots here, as you can see, right? But the way that processes are implemented has changed simply because we have been shrinking down the die features so much. The clock frequency in particular has not been going up anymore since the early 2000s, which means that the serial execution performance is roughly constant. That's not entirely true, of course, but it's not automatically much faster, or it's not getting much faster your code if you have a serial code. You can't just wait 2 years and it gets faster. So the performance increase is really due to the increase of CPU cores per processor, right? And you can't simply wait to get code runs faster. You must write parallel code. That's basically the gist of it. The frequency has here plateaued, and you have many more cores now. So whatever you do, whether it's CPUs or GPUs, you have to write parallel code. And so this is also a little bit outdated. I don't have new data for this, unfortunately, but it really shows you trends that have been going on and are still true. So what you see on the left and on the right is the floating point performance of CPUs and GPUs. So blue is representative like Intel Xeon CPUs, and red and green is AMD and Nvidia GPUs. And so you can see that you have a significantly higher floating point performance on GPUs. That is true for 32-bit floats, so often referred to as single precision floating point variables or data. Also for gaming GPUs, so cheap gaming GPUs that you see in here, like GTX Titan, and these are older ones, right? But nowadays you would have a lot of gaming GPUs. They're hard to get by now because they're all basically bought up on the market by cryptocurrency miners, as far as I understand. But if you get your hand on those, you get a lot of floating point performance for cheap, at least 32 bits. If you need 64-bit floats, you need to go to data center GPUs. Like here is the Tesla P100. That's what's in Comet, the newer GPUs in Comet, and we have newer ones, the Volta V100 in Expanse. And it's not only the floating point performance. So on the left, you see the memory bandwidth, and you see there's a pretty big gap between CPUs and GPUs, and that means the speed with which you can move data between the GPU memory. So the GPU has its own RAM, its own memory to the GPU processor versus the CPU RAM to the CPU processor. And that's very important because many, or I would say probably the major part of algorithms implemented are not floating point performance bound, but memory bandwidth bound, which means it doesn't help you if the processor is faster if you can't get the data to compute or store the data back, output data. And in terms of power consumption, it's sort of like comparable. It depends on the GPU type and the processor type, but a GPU consumes approximately 1.5 to 2 times as much as a CPU. So you have to factor that in because, of course, power is very expensive as well, right? So that's a comparison between CPUs and GPUs. So that's basically a state-of-the-art dual-socket into Xeon type CPUs. Each of those CPUs has 28 cores, and here you would have the Nvidia Tesla V100. These type of GPUs we have on Expanse, right? So Expanse actually has 4 of those GPUs per node, and they are not like this PCI Express connected. I'll show you that later. And so you can see that if you compare like a dual socket, here both 56 cores per node, you get around 4 teraflops of performance versus 3.5 times that with 2 GPUs, and the peak for the single precision is of course the factor is the same. I've seen many codes that make good use of those single precision floating point performance of the GPUs, less so on CPUs. There's something else in newer GPUs that's half precision, and that's often used in machine learning applications, specifically deep learning applications that can actually efficiently use half precision. So that means 16-bit floats. That's often not possible for scientific applications where you need higher, larger precision for higher accuracy, but many deep learning applications can exploit that. And you see, then you can get a really huge performance. So that's why GPUs are very popular for machine learning, deep learning applications in particular. And then the memory bandwidth, of course, is much higher. And I put on here the PCI Express bandwidth. So you see that, if you have to go through the PCI Express bus to get data from your CPU memory to the GPU, it's much slower, right? So that's something to keep in mind. And the code you write, is it portable? I would say yes. There's OpenACC and OpenCL. I'm not going to talk about OpenCL though. I'm going to introduce briefly Cuda. That's Nvidia specific, so in that sense it's not portable, but it's been around for so long that and there's like a software out there that helps you also to translate Cuda code into programming languages that work with AMD GPUs or Intel GPUs now as well. So in some sense, there's portability out there. It's not too much to worry about. And I just want to point out, how supercomputers or processors in general have developed over the last 20 years here, right? So if you look at the number one of the top 500 list that was at Lawrence Livermore National Lab ASCII-wise, the supercomputer, it had a total performance of 12.3 teraflops. The machine cost $110 million in 2001, so 20 years ago, right? So really expensive. Now, if you compare that to Expanse, it's a much smaller machine in size. It doesn't fill the entire data center. It has 728 CPU nodes that give us 3.4 petaflops, right? So that's from teraflops to petaflops, right? The aggregate performance. And there are 52 GPU nodes, each with 4 Nvidia V100 GPUs. And those 52 nodes, right, give us 1.6 petaflops in double precision, or 3.3 petaflops in single precision GPU performance. And that's all for a cost of $10 million US, right? If you want to build your own little supercomputer, you can do that. You buy these gaming GPUs, and that costs you around $2,000 if you get them at retail price. And you see, you get 10% of the double precision performance of the entire supercomputer here from 20 years ago. So it's pretty impressive, right? And you get 10 times the performance in single precision as the supercomputer. So if you have an algorithm that you can implement efficiently in single precision, you can run 10 times as many simulations on this single, desktop workstation as compared to that supercomputer 20 years ago. So I hope you all are going to make great discoveries, scientific discoveries with all that computing power that you have at your hands. GPU accelerated software now covers literally all the fields. Nvidia has a lot of information on their website. It's actually quite good. So if you go there and you want to explore a little bit, you can find lots of software in your field. You might find something new or some inspirations and examples. I just wanted to briefly talk about machine learning and GPUs, just a single slide, and why that actually is such a big thing for GPUs at the moment. So what you do in machine learning, what you want to build is a predictive model. So you have some data here that you train on, right? And you have a model that you implement. And so that gives you your machine learning algorithm, and then with some input data that's unknown, you make a prediction, and then you actually check whether that prediction, so during the training, you check whether the prediction comes out okay, and once you're satisfied, you can then use that algorithm to predict, of course, results for unknown data. And so deep learning is the thing that works so well on GPUs. And that's basically a neural network with many hidden layers simplified. And so you have a neural network where you have like this input layer and an output layer, and then you have these nodes in between. And this is an example of a fully connected neural network. And if you look at a deep neural network, simplified, basically all it is, you have many hidden layers, right? And with that, you have many more variables, and you potentially, have a high dimensional function that can fit practically anything. That's the idea, essentially, right? So if you have the right feature vectors here. If you write down the equations and look at how it looks like, there's a lot of matrix multiplications, so tensor operations involved. And GPUs are just very efficient at these, because if you go back to the history of where GPUs come from, and then you think about how 3D graphics is implemented, there's a lot of 4x4 matrix algebra. So they have very efficient hardware to do these matrix multiplications. And in addition, as I said, GPUs now implement in hardware half precision arithmetic that can be used for many machine learning applications, at least at the inference stage. So when you make your predictions for the training, often you have to use the at least 32-bit floats. It depends a little bit on the problem. And then the newer architectures like the Nvidia Volta and the successors like the Ampere architectures, they introduce tensor cores. And that's dedicated hardware for mixed precision matrix multiplies. So really super efficient. And if you have a machine learning framework, then it's actually really simple because PyTorch or TensorFlow, you just have to tell them to use the GPUs, and they will generate the code for the GPUs and execute on the GPUs as opposed to the CPU. So it's pretty straightforward. So you don't really need to know much about GPU programming in that sense. I want to quickly show you some benchmarks, whether you like benchmarks or not. You can often show data that you can tweak benchmarks in a way that whatever you want to show looks good for you. So that you have to be a little bit careful with benchmarks. But I just picked two, three examples from my field. I'm a chemist by background, so quantum chemistry, molecular dynamics background. And so this is an example. This was the earliest real code, and it's still around. That high performance code that does quantum chemistry calculations on GPUs, and you can see, so this is an old comparison from many years ago from their website, but a single gaming GPU versus a single CPU core. And back then there were not so many cores in each CPU in any case, but you see, in particular for larger calculations, larger molecules, you can have significant speed up, showing speed ups here around 30 to 176. And so even if you have a multi-core CPU, you can't beat a single GPU here. Similar, we have our own quantum chemistry code, Quick, that we are developing, and you see the same. There's a certain piece to the quantum mechanical Hamiltonian that we compute, and for different parts of the calculation, we see also speed ups anywhere between like 50 and 200. And the important part is here on the right plot, where you see the time logarithmically and the number of CPU cores, right? So this was a benchmark that was run on up to 40 CPU cores with an MPI parallel implementation. And so you see these are two pieces of the calculation that are computationally expensive. The important part is the dashed line. That's the time to solution on the GPU, and it's faster than running on a full compute node, right? So a single GPU is faster than single compute node. Molecular dynamics is another example where we have to simulate the interactions of particles and there's thousands and thousands of atoms in these simulations that we are doing, and the relevant timescales that we want to achieve is somewhere here in the micro to millisecond second timescale, but the time steps we have to take is in the femtosecond timescale. And one time step has to be done after another one. So if we want to finish with these simulations within a reasonable amount of time, the simulations have to be really fast at each time step. And this is performance data benchmarked for the AMBER and D codes that we have been developing on CPUs here. So this is up to 36 cores, and this is on a single GPU. So you see, it can be a single GPU. This is the V100. That's the GPU that's deployed in Expanse. We effectively get like 25 times as much computational throughput as on a single CPU. Right? There's probably some leeway, some room to improve the CPU code, but not much. And this is because also partially we exploit single precision. Now, what's the problem with that? And that's why you are all here. Is literally, you want to use GPUs because you want to cut down on your electricity costs and finish your simulation faster. And and then the manager asks you, why is your part taking so long? And it has to do with the GPU architecture. You can't just, take your code and compile it for the GPU. You have to actually develop algorithms that run effectively efficiently on the GPU. And so what's depicted here on the left is schematically, and on the right, you see for the CPU and for a GPU on the right, on the left for the CPU. This is the real estate. So the depicted the area of your chip, of the processor, right? And so in a CPU, you have a lot of cache memory. You have a lot of control units. So you have lots of sophisticated hardware in there, and then only few processing cores, arithmetic logical units here. So the CPU does a lot of things for you, like multi-level caching, prefetching, branch predictions, all these things that happen under the hood that make your code run as fast as possible on a single core. Now, that's very different on a GPU. There's much less control logic, but in exchange, you have many more compute cores that are much more simplistic. Those are packaged into individual multiprocessors. So it's a little bit as if you would have like several multi-core processors on in each GPU. And these processors, the cores, they operate in lockstep. So there's a single instruction issued for multiple threads, so the SIMT architecture. And it does also vectorized loads and stores to memory, and you need to manage the memory hierarchy. Now, operating in lockstep, that means you need to write a parallel algorithm that exploits that and can exploit that. So here, I'm showing you a very, very old graphic from Nvidia. So this is like 2008, and you wonder, oh, this is very old what he's showing. But so this was the first data center GPU server from Nvidia. I'm showing this because there's not much in principle that has changed on the very basics, right? So this is your GPU processor. And they had the same type of processor either in a PCI Express card or in chips. In this case, they were connected via PCI Express bus. So you can see here 2 graphics cards in there as far as I remember. And each of those GPU processors has several multiprocessors, and each of these multiprocessors, right, has its own instruction cache and there's a multi-thread issuer that issues, the instructions to the processors. You have the single precision compute cores, you have double precision compute cores, special function units, and shared memory that is shared for all those processors that are sitting on one of those multiprocessors. And so one of the important things is this architecture can handle many more threads than processing cores, and that's one way actually to hide latency. The hardware has changed over the years, but the basics have remained the same. So, if I say the hardware characteristics change across GPU models and for generations, that's right. But that doesn't have to affect the way with which you write your code. So, of course, GPUs have improved similar to GPUs. But one thing that's important is, memory hierarchy is exposed, and it doesn't have to be. There are ways to get around that, but partially. But you have to be aware about CPU and GPU memory, and then there are other types of memories in the GPU that you can use. So unified memory is something that exists that helps you. You don't have to distinguish between CPU and GPU memory, but of course, behind the scenes, the data still needs to be copied forth and back. And then there's, of course, Nvidia and AMD, and we have Nvidia processors on Expanse. So we'll talk about those, and maybe I'll just skip this because we don't have much time. different types of gaming GPUs. And in any case, so what you want to do is you never write code with any assumption for how many threads it will use. There are functions in Cuda to query the hardware, and you launch more threads than processing cores and to hide memory latency. And if you can avoid double precision, do avoid it, because then you get higher performance. But of course, you need to make sure that this doesn't affect the accuracy of your numerical simulations. A brief overview, there's OpenCL that you can use. It works for Nvidia and AMD GPUs. There's Cuda, that's proprietary, but open source. So Nvidia, nothing's hidden there. It works only for Nvidia GPUs, but it's the de facto standard for high performance code. And then there's OpenACC, that's accelerator directives. For Nvidia and AMD, efficient implementation at the moment only for Nvidia. It works with C, C++, and Fortran, similar to OpenMP. And then OpenMP also supports GPUs, but it's not really mature yet. So you might want to, follow the developments there if you're interested. Now, if we go to Nvidia, we have Nvidia GPUs. You have a lot of libraries available for deep learning, QDNN, fast Fourier transforms, linear algebra, and so on. And there's support for basically all, many programming languages. Natively C, C++, because Cuda is an extension to C, and but also Fortran, and then there are wrappers for Java, Python, and of course directive-based programming. And yeah, basically any Nvidia GPU is Cuda enabled. So if you write code that runs on Expanse, it will run also on your desktop computer or laptop, depending on what type of GPU you have. Development tools, there's a so-called Cuda Toolkit that's free, contains the Cuda C compiler, libraries, debugging tools. There's a Cuda debugger, Cuda GDB, and Cuda memcheck for memory leaks. Then there's profiling tools, NVProf, NVVT. So NVProf is the command line profiler. That's a visual profiler that gives you a visual overview. These are being slowly phased out by NVIDIA in favor of their Insight systems and compute. So Insight systems is the high-level profiling tool. It gives an overview over the entire runtime of the program, shows you, when CPU code is running, when memory copies happen, which kernels run at which time. And then with Insight Compute, you can get more statistics and data about individual kernels. If you get down into actually optimizing individual functions, so kernels or functions that you've written for your GPU. And this I always like very much, in particular if you're a beginner, code samples which are contained in there. And I hope I'll get to that once I get there. That's where you can get them. Now, if you are on Expanse, if you are on a GPU node, what you have to do, all you have to do is you have to load the module. I always recommend to say module purge first to remove all the modules, and then module reset, because we have different types of modules on the CPU nodes and the GPU nodes. So you want to make sure there's nothing left over from your configuration from the loading node, etc. So just it's safe to put these two things in there and then explicitly load the modules that you want to have. So module load Cuda will load Cuda 11. Cuda 10.2 is also available, and the code samples, unfortunately, are included and work only for Cuda 10.2 in the installation on Expanse. Then there's also the Nvidia Hpc Sdk that's also available. This will replace the Cuda toolkit in the future, and it's basically the Cuda toolkit plus some extras, and those extras are the Nvidia C, C++, and Fortran compilers. Those used to be PGI compilers. There's also, and the PGI compilers are also available on Expanse. But in going forward, those are being merged because NVIDIA bought PGI many years ago, and now all the software infrastructure and software development infrastructure is being put into a single package. And very simple, you just say module load NVIDIA Hpc, and then it's available to you. And yeah, so okay, so how would you write or develop applications? So that's what I'm going to do. I'm going to show you quickly libraries, then Cuda, then OpenACC, and then we'll look at how to get into compute nodes on Expanse. So if you have libraries available, if you have a code that calls libraries, say blast functions, for instance, or FFTs, or you can just use those libraries, and that should be pretty straightforward as a drop-in replacement, because these follow standard APIs. So minimal code changes are required, and of course, do use those because they are very performant, tuned, and high-quality implementations. So don't write your own matrix multiplication apart from learning. I have a matrix multiplication example in here that I'll very quickly go over with you just so you get an idea how Cuda code looks like. If you go to this website, there's a list and lots of explanations of all sorts of libraries that are available. So, if you have a C, C++, or Fortran code and you want to use a library, it's pretty simple, right? Imagine you have a stack speed that's a blast function, that's a signal precision a times x plus y. It's a vector addition. You just replace it with a call to qblaststack and then you have to do some additional things, managing data locality, meaning you need to allocate memory on your GPU, you need to transfer the input data to the GPU, and there are qblast functions for that as well. So you can use Cuda or wrappers specifically for vectors or arrays or via qblast, and then you just rebuild your code and link against that library. And so imagine you have this function here, a call to Saxby, and it's the size of your problem. So you compute y equals a times x plus y. So y and x are input, y is also output. And yeah, this is just drives in the arrays and the last function call. Now, all you do is you have to create it with replace it with a call to qblast Saxby. And pass it a handle that basically has the there's some memory allocations and similar things on the GPU. You can create that handle and then destroy it again. Then you call the allocation of memory allocation, where you need to know how much memory you need, and you store that in some pointers here on the device. It's often you see that prefix the variables with a d underscore to tell the programmer to understand that, okay, d is actually a pointer to memory on the GPU, right? And then you transfer the data from the CPU, so you had it in X, right? You transfer it to the pointer to the memory address on the GPU, and you use this qblast set vector function for that. Then you call your function, and then you copy the data back, and that's it. So as simple as that, you can get GPU acceleration if you have a compute-intensive part of your code that you want to replace with library implementation. That's to use libraries. Now, what about writing your own code? Okay, there's Cuda C. Here's again a link for you to explore. It's a solution that runs C seamlessly on GPUs, right? As I said, this is de facto standard high performance code on Nvidia GPUs, but of course, while the extensions to C are, modest, it requires major rewriting of code. So it can be easy in some cases, but it's in particular if you have a larger code base, can be a lot of work. There's also Cuda Fortran that has Cuda extensions for Fortran. It was developed by PGI and it's available in the PGI Fortran compiler, but also now in the Nvidia Fortran compiler. And there's some recommended reading here, about the Nvidia Hpc Sdk, then Cuda C. The programming guide is actually pretty good about Cuda Fortran. And then here, this website, the gpuhackathons.org, there's a lot of resources. We just had a hackathon organized also at SDSC, but there are many throughout the year, so that must be something you could be interested in if you have code that you want to port. And heterogeneous computing is called heterogeneous because you have two types of processors in your system, CPUs and GPUs. So that's literally how the flow looks like. You have code on the CPU, serial code, could be parallel code to MPI or OpenMP. And then you have this parallel code in a kernel that launches on the device, and that's depicted here, a grid of blocks of threads, right? So that's Cuda nomenclature. then those blocks get mapped onto the different multiprocessors in the GPU, and they run in parallel. And then you return control back to the host, and then you launch maybe another kernel that does some different computation, similar to the library function call that we just looked at. So serial parallel code, and that's how the processing flow looks like, right? You have your CPU, it's connected via PCI bus or some other interconnect to the GPU. You have to be aware that transferring data from here to here is relatively slow. And that's the device, that's your GPU with all these multi-processors on there that I talked about before. And so you copy data from the CPU to the GPU, and then you run your program on the GPU, and then you copy the results back. Okay, so that's basically what you have to do. Now, how to implement that? First, about unified memory, you don't have to do this distinction. So there's the concept of unified memory that you can use, that this pool of shared memory, memory that is shared between host and device, and that helps you programming faster, right? The memory copies still happen under the hood, so you need to be aware of that. And that's also a way to improve code after you've done a first implementation with unified memory, potentially to explicitly manage that memory. Now, if we think about Cuda, you see a lot of nomenclature, and so I mentioned kernel before. What is a kernel? A kernel is a piece of code, typically a function that can be executed on the GPU. So it's a function that you write that then is supposed to be executed on the GPU. And this kernel code operates in lockstep on the multiprocessors of the GPU in parallel, right? So many compute cores do the same operation at the same time. And on Nvidia GPUs, that happens in so-called warps of threads, currently consisting of 32 threads, right? And that's basically a single instruction, multiple thread architecture. And a thread is just an execution of a kernel with a given index, right? So that kernel is basically launched many times. That function is executed many times, and each instance of that function knows in this grid block that I alluded to before where it is. It has an index for that. And with that, you can access subsets of the data. Now, the block that I showed before is just a collection of the threads that are grouped into blocks, and that's done because they're guaranteed to execute on the same multiprocessor. And with that, the threads can synchronize and share data, and so you can exploit this in the algorithms that you implement. While blocks that are run on different multiprocessors, they can't see, they don't know what the other processor is currently operating on. And the grid is just an entirety of all the blocks. So that's just Cuda nomenclature. And so, you know the size of the grid and the size of each block. You know the number of total running threads. Here depicted again, you have the grid with your blocks of threads. And like I said, the blocks map to the multiprocessors. So block 00 could execute on one multiprocessor, while at the same time, block 10 could execute on a second multiprocessor, and so forth. And the threads, then, within those blocks, there's always 32 that execute the same operation at the same time in a so-called warp, right? So in this example here, let me talk first about the built-in variables, right? So you have the variables here that you can query in order to understand which ID each of those threads has, right? So there's the grid dimension, and these are three-dimensional variables. So you have an X, Y, and Z component. Z component for grid dimension is unused. So you can have a two-dimensional grid and a three-dimensional block. And the reason for having a three-dimensional block is because this way you can map it easier in your algorithms. You can think about, maybe you want to use a two-dimensional block indices if you have a problem with a two-dimensional matrix, right? Matrix multiplication, something like that. Or if you have volumetric data, then maybe it's easier for you to use X, Y, and Z to index points in a three-dimensional grid, for instance. And so we know the block dimensions. Oh yeah, sorry, I didn't talk about. So this is a block ID, right? So this block here would have an ID 00, and this one an ID 10. And then within that block, you have the thread IDs for each thread. So this thread here has ID 00, this thread has an ID 10, this one here 01, and so forth. So with that, you can compute the size, the number of all your threads, and you can compute your individual, each thread knows where in this grid it's sitting. In this example, just for depicting here, you have 3 times 2 blocks, so 6 blocks, 3 times 2, and then each block has 4 times 3 threads, so 12. You have a total of 72 threads running. Of course, you want to launch many more, and you should always use at least 32 or a multiple of 32 threads in each block, because 32 is the magic number of cores that always will do the same operation at the same time. Then if you write a function, you have the underscore global underscore keyword that is a function now that executes on a device, but can be called from the host. And so that's basically a kernel. So this is just like C code that you see here. And you see you have here a simple while loop, for instance, that would be a vector addition. Imagine you're passing in A and B and C as pointers, and those point to arrays, right, to a vector. And you want to do a vector addition. And now what you do is you compute your index, my thread index, as an offset in that grid block using those variables that I showed you before. And I know that this is hard to follow now because I'm going very fast, but I just want to show you the basics. And then the stride, right? So that's basically the total number of all the threads that are running. And then all you do is each thread computes that sum A plus B for a different element of that vector, right? And stores it back in the result vector. So that means you're doing this in parallel with all the threads that you have been launching, right? On as many processes and compute cores that you have available on the GPU. And then, so each thread at some point, needs to increase its counter and to operate on the elements of the vector that have not been operated on, and will stop once we reach the end of the vector. And that's the very basics of how you implement like parallel kernels on a GPU. And then of course you have to call them from the CPU code, right? In addition to that, you have the memory functions like allocation, free memory, memory copies. It's equivalent to Cuda C malloc, free and mem copy. And so if you have a kernel like that, then you can launch it from your CPU code. And all you have to do is you have to add this launch configuration here in this triple angle brackets, and where you tell basically with this there's a variable type dim3 that you can use where you specify the grid dimensions, the number of blocks in X, Y, and Z dimension, and the number of threads, so the block size in X, Y, and Z dimension. And that of course has to match the implementation of your kernel here, right? This is again the memory hierarchy, depicting again what I've been talking about. You have so-called global memory, that is the GPU RAM that can be seen by all your threads on the GPU. And then you have the shared memory here. This is visible by all the threads in each block. So the thread 00 and thread 10 can store data and read from the same shared memory, but they cannot do that for thread 00 and 10 in this other block here, right? So that's something you have to be aware of. And you want to use shared memory because it's fast, much faster than global memory. It's like a cache on the chip. There's also automated cache, and then there's registers in local memory, and constant memory is important, where you can store, for instance, like if you have natural constants or similar things. And when you write code, what you want to do is you want to avoid data transfers between the CPU and the GPU because these are slow. You want to minimize access to global memory, for instance, caching data in that shared memory space by tiling data, right? That fits into the shared memory, and then so each data subset will be operated on by a single thread block. So you decompose your problem into smaller problems that then, you operate in parallel, or within those smaller problems, you also work in parallel with your threads in a block. And so you load that subset of data from global to shared memory, and then you perform the computations, and then you copy the results back to the global memory. Now, I put too much into this presentation, so I will skip over the matrix multiplication example because it's just too much also to follow, and I want to show you OpenACC and of course Expanse. But just to give you an idea, sorry, this was in, you have a matrix multiplication kernel. So that's what you would do. Imagine if you do a matrix multiplication. The way you'd implement that, if you were to do this, is and here I'm actually simplifying something here in this scheme and in the code that's on those slides. You make an assumption that you have a block size here, you know, and for each block you have several threads running, and that block size must be a multiple, or the size of that result matrix must be a multiple of the block size in X and Y dimension. And then we launch a single thread to compute each element. So you have one thread that does this dot product between, you know, this row vector and this column vector. And so what that means is that each thread computes one of those dot products. And in order to have good performance for a kernel like that, what you need to do is you load these submatrices, subblocks here basically into shared memory. So this subblock and this subblock, and then you do the matrix multiplication. And then you store the data back, and then you load the next subblock and the next subblock, and you do the matrix multiplication. So you do this cache blocking. And, you know, I have this here on the slide, but this was, you know, sorry, I should take these things out because it's a little bit hard to go through quickly. It's not a difficult example, but you can find that also in the Cuda documentation. That's where I actually took also that figure from, right? And that would be an example of why you want to have two-dimensional grids and blocks, because you can index easier into a matrix, right? Makes it easier. In reality, we would not want to write a matrix multiplication because we have a Cuda class function implementation, linear algebra implementation that's very efficient. So this was now very complex, but what about something simpler? Something simpler as OpenACC is this open standard for expressing accelerated parallelism, and it's designed to make porting to GPUs easy, quick, and portable, right? Because in principle, you don't write code that is specific for a certain vendor like Cuda for Nvidia. So OpenMP-like compiler directives works with Fortran, C, C++. It's fully supported by Nvidia and Cray compilers. On Cray's, there's partial support by GNU compilers, like I mentioned before. So it's pretty, yeah, I would say future-proof as well. And OpenMP also works, but it's not there yet. And you know, these things might just merge at some point, the standards. There's the PGI compilers that we can use on Expanse. They also come with a PGProf performance compiler and also some OpenACC code samples. You can also use the Nvidia Hpc Sdk, right? That's, I mentioned that before, that, you know, Cuda Toolkit and the PGI compilers are merging effectively. In future releases, there's probably going to be only the Nvidia Hpc Sdk. And again, you do the same module purge, module reset, and then if the module load PGI, you get the PGI compiler, and it loads by default version 20.4 at the moment. But if for whatever reason you need an older version, there are older versions installed as well on Expanse. And literally, I only have this one slide here to show you some code. But you know, we had that example of SAXPY, this function. And now, if you were to implement this function yourself manually, of course, you don't want to do that because, you know, you have the BLAS functions for that. But imagine you had implemented that. This is your function. On the left, it's just in C, and the right in Fortran. I'll just go over here. It's a vector addition, so you have this for loop, right? Now, the vector addition, like we've seen before is very well suited to run in parallel on the GPU because you can add each element of that vector independently of each other. And you have this for loop here, or do loop in Fortran. And all you have to do in principle is insert this pragma ACC kernels. And there's, of course, much more to this, but this is the most first and simple thing you can do. And this will instruct the OpenACC compiler to generate a kernel for this loop that executes in parallel on the GPU. So you don't have to do all this programming yourself, right? Allocating memory, moving data, implementing the kernel, launching the kernel from the CPU. It also has the advantage that this code just keeps compiling on with your CPU compiler because you've just inserted effectively pragmas that are comments into the code, right? And that's all you have to do in principle, right? Of course, you have to help the compiler, and there's much more to it, similar to OpenMP. So in Fortran, so you have these directives that are often paired with a matching end directive surrounding a structured code block, right? Like this for loop, you have a structured code block following this pragma ACC directive, for instance, right? That we had here on the slide before, this pragma ACC kernel in this case. And so you have this kernels constructed, instructs the compiler to generate a kernel that computes on the GPU. Then you have clauses that you can add, like if a certain condition is met and so on. And then you have, for instance, like data clauses, like copy in, and list. Here's a list of variables, right? Copy out, create present. And, like I've shown you before, the GPU has its own memory. And this is exactly how you tell the compiler how to handle memory copies, right? And sometimes the compiler does the right thing, but more often than not, it will not, and you get bad performance, and you have to actually tell the compiler that you want to copy in the data to the GPU, or the data is already on the GPU and so on, and with that you can use data clauses. So you have to help the compiler often. And there's an example that I want to show you here. Is a stencil operation effectively. It's an algorithm, a Laplace. So it's a Laplace equation via Jacobi iteration, where you have multiple iterations for time steps in your algorithm. So at step k plus 1, right? You have the data. So here stored in a two-dimensional array. Imagine you have a huge grid. So here I'm looking only at one grid point and its neighbors, but imagine you have thousands of two-dimensional grid. You have the data and you just compute the average from the previous time step, and that gives you the result at the next time step, and that will slowly converge. And this is the code, right, written for the CPU, right? So you have a loop where so what you do is you iterate until basically the matrix elements don't change anymore between the steps, right? So then the algorithm is converged. That's the outer while loop here, and so you compute the error. That's your threshold for convergence. So first you set it to 0, and then here we do our update. So we have this loop. We go through x and y dimensions, I and j, and then so we have the array A, and we just do the sum of the neighboring elements, I plus 1, I minus 1, j minus 1, j plus 1, quarter of that, so the average, and stores it in the new matrix, and then we check the difference between the old matrix and the new matrix and store the maximum error, and we basically stop here when our error is smaller than a tolerance, or once we hit a maximum number of iterations. So now we want to do this on the GPU in parallel, right? Here we just swap the array, so that's not so important. And what you want to do is we just say, okay, do this on the GPU. And then you can compile this code with a Portland group compiler, and you just tell it, okay, minus ACC, this is an ACC, so open ACC code. This is PGF94 Fortran code. You could use PGCC for C code, etc. And then you get some information here with minus m info equals x. Well, it tells you actually what it does. It generates this copy operations. It generates reduction operation. Here's some information about, stocks and threads and so on. So you see, it uses the same nomenclature, so internally it translates it basically into Cuda code. And this is the performance we get for this code on Expanse GPU node, with a corresponding compiler flags. This is limited, I don't remember, 10,000 iterations of certain size, but I'm executing literally the same code on the CPU and the GPU. And this is using OpenMP parallelization. So instead of OpenACC, there's an OpenMP pragmas in there. And you see we get a decent speed up, goes down from 40 to 20 seconds, 10 to 7. Speed up gets worse and worse, of course, the more threads you have. Now, if I use OpenACC, it gets really slow. And so that's really bad. So what happened is you can switch on the PGI ACC time environment variable. You set that to 1 and you get profile. You need to profile your code. And what you see is that 20 seconds spent on something that is just data copy transfers, right? And then 1.5 seconds here on the compute. That's actually not, this profile is not from Expanse, but you get the idea. And what's happening is in this loop that we have in each of those iterations, we copy the data to the GPU. And then after that, we copy it back because the compiler has no way of knowing that, once it's done with this loop, it can keep the data on the GPU. So we have to help the compiler and tell it here with a data clause that, copy A to the GPU, allocate memory for A new, right? So now the compiler knows, oh, while I'm not done, I always just keep the data on the GPU for my iteration, right? And if I do that, now all the magic happened, and it executes in 1 second. So it's almost 7 times as fast as 8 cores, right? And that's with that little change. So it was a huge speed up with respect to the, you see like a 42 times speed up, 40 speed up, X speed up versus the CPU code. The CPU code with a very, very little effort. There's more to OpenACC, but I'll skip that because what I want to show you is Expanse. We're almost at the end of the hour. You give me maybe 2 or 3 minutes. I'll show you very quickly how to get onto Expanse GPU nodes and how to use Nvidia Cuda compilers and OpenACC. The important thing is we have 52 GPU nodes, a total of 208 GPUs. And that's a little bit here, some more details about how the Expanse looks like. I think all of these things have been explained already in a different webinar. Important piece here is, that's schematically how a compute node looks like. So you see these GPUs, they're not sitting on a PCI Express bus. They are like this V100 SXM2 GPUs. They are like regular processors, and there's 4 GPUs here in the compute. And here in the back, you'd have the CPUs, and then these have special interconnects via NVLink. So that's actually a really fast interconnect among the GPUs that you can exploit if you write parallel GPU code. There's more information at the user guide, Expanse user guide. Now, if you log in, so you get onto Expanse, just SSH into Expanse, the GPU nodes, if you write a batch shell script, you access them via 2 different types of partitions. You have a partition that's called GPU, then you get an entire node with 4 GPUs, or you can use a GPU shared queue that you can request 1, 2, 3 GPUs, for instance, if you don't need 4 GPUs. You do have to always specify the number of GPUs. And so this here is an example where you use srun to get interactive access to a compute node. And like you see here on a shared GPU node with a single node I want to have with a single GPU, and then I'm asking for a single task and 10 CPUs per task. So that's important if you, for instance, are running a OpenMP code in combination with a GPU. I'm asking here for 80 GB of memory. Don't ask for more than a quarter of the memory per GPU, otherwise you will be charged for 2 GPUs or 3 or 4, depending on how much memory you choose, right? Proportionally. And the time, and then I just want to have a bash shell, and then job starts, I'm on a GPU node here. Now, if I'm on a GPU node.
Andy, can I jump in here just for a moment? We're
Yes.
at the top of the hour, so some people may need to drop off. I just wanted to remind people we are recording this and we'll keep the recording available. And there was one question in the chat. I want to make sure we got that covered before, if he has to drop off. But yeah,
okay.
Keep going because I'm going to continue.
I'm almost at the end. There's not much more. It's literally 1 or 2 minutes and I'm done. So if people want to hang on, I'd be happy. And I apologize for taking longer than the hour. So this is what I wanted to say. Don't ask for more than proportional resources. You have 4 GPUs per node, 40 CPU cores, and 374 GB of RAM. So if you ask for 40 CPU cores, you will be charged for 4 GPUs because nobody else can get on that node anymore. And then if you want to load the modules, you say module purge, module reset. Sorry, this one you can load, you don't have to. But important piece, you can load Cuda, PGI, and or Nvidia Hpc. So either these two together or any one of those two, or alternatively Nvidia Hpc, depending on which compilers you want to use. And so if you do that and you have the Cuda compiler loaded, it should be available. You type nvcc-version, it should show you the version of the compiler. So the same for the PGI compilers, there's like PGCC, PGF90, and PG, keep forgetting how it's called, the C++ compiler. This is the interactive access. I'm on a GPU node now. NVIDIA SMI, the system management interface, will give you information about the GPU. You'll see there's a V100, S6, and 2, and so on. It will tell you if there are any processes running. At the moment, I don't have anything running. No running processes found. There should be no other jobs running because you get individual access to each GPU. So they're configured such a way that the Cuda runtime sees only the GPU that belongs to you. Okay. The Cuda toolkit samples, they are also available here in this directory. For this, you have to load the Cuda 10.2 version to work. If you copy those into your home directory, that's what I've done here. There's different types of samples, from simple examples, etc. So the simple examples and utilities are useful. You can then just compile those if you have loaded the Cuda toolkit. And this will take a while, or you compile them individually. So you can go into one of those subdirectories and compile them. So here, if I compile the device query function, and you can always look at those source codes, and that's why these examples are so nice. It queries information about the GPU, right? So for instance, if I start this, call the device query, it tells me I have a single V100 GPU there and gives information about the memory, the CUDA cores available, and so forth. And that's the very last thing. This is the last slide. If you go to the simple examples, because I mentioned matrix multiplication, there's a handwritten matrix multiplication that has all these optimizations in there. And you see, if you run that, it gives you a performance of 3.3 teraflops approximately. Now, there's another example that uses QBLAS, the QBLAS function for matrix multiplication, and that gives you like 7.6 teraflops. So you see that, if you want to use libraries, you always, these are highly optimized, but much faster than the handwritten matrix multiplication here. And yeah, with that, I'm at the end, and thank you for bearing with me. Now, if there was a question, I don't know, I don't see. Jeff, could you tell me what the question is, and I can try to answer?
Yeah, Gregory Wolf was asking, he's an experienced programmer of single GPU machines using CUDA. What does he need to look out for or consider when developing for Expanse?
Okay. So if you're experienced writing, let me go here to the last slide. If you are an experienced programmer, so it depends on the language that you've been using, but there are different ways to program multiple GPUs. One thing is to use CUDA streams, where if you have CUDA code, you can use CUDA streams, and then you can launch code or kernels, execute kernels on different GPUs. You can transfer part of your data to one GPU, part of the other GPU, and then there are of course, also communication that has to happen between the GPUs, and there are libraries for communication between the GPUs from Nvidia. The other option, obviously, is to use OpenMP. You write a parallel code, CPU parallel code, and you have individual threads handling individual GPUs. And finally, you can use MPI. And what you always have to watch out for is whether you can decompose your problem without having to communicate between the GPUs or not, and that you don't similar things that if you write parallel code that uses multiple nodes, because the communication step at some point might be limiting, and if you copy data forth and back between the CPU and the GPU memory, that could be just rate limiting. Those are some of the considerations to consider, yeah, I hope that answers the question, but I don't know if there are further questions that we have to discuss.
Yeah, and if anyone wants to unmute, that's fine as well. There was another question compared to Cuda, how much performance is lost when using OpenACC?
Oh, good question. OpenACC can be very efficient. I wouldn't say how much performance is lost, because usually you don't translate a Cuda code into OpenACC. Usually you go the other way. The big question is how much more effort is it to write a Cuda code in OpenACC, because the most expensive piece typically is developer time. Unless you get to some code that like our AMD simulation code that's literally burning, I don't know, a few % of all the available compute power on the XC resources. So that makes sense to actually really put a lot of effort into porting. So OpenACC is a good way to start porting code if you have only CPU code, and it can be high performant, but it's not a magical bullet. So you often have to restructure the code, and once you get into doing that, you could potentially write Cuda kernels that then can be faster. Yeah. But it's not a bad place to start. It's a good place to start. We'll stop share here. So, don't know if there are any other questions.
No more in the chat.
Okay. Well,
does anyone have any other questions? If not, going once, going twice. Well, thanks very much, Andy. This was very interesting and useful, and hopefully the audience got a lot out of it. We will be making the recording available as soon as possible after Zoom finishes the transcription. Other than that, thanks everyone for joining. Have a great rest of your day, and we'll call it a day. Thanks again, Andy.
Thank you very much, everybody.
Bye, everyone.
Goodbye.